from the beginning. So if you refresh your contents page, go into D2L, content, find Unit 1, PowerPoints. Unit 1 is going to consist mostly of these three PowerPoints, 2, 3, and 4. Why? Because Chapter 1 in most textbooks is a little bit tedious. What is a computer? Why are you a programmer? That kind of stuff. So we're going to take a look at Chapter 1, and then we're not going to talk about it very much. If you have the book, I want you to read it, but why program? Okay, what is a computer? It's a programmable machine designed to follow instructions. What separates a computer from a primitive calculator? A calculator can do math, but it can't follow a sequence of instructions. You have to sit there and type in all the numbers. If you made a calculator with a paper tape that you fed into it and it followed all those instructions, and then maybe it wrote the answers out on another paper tape, all of a sudden you have a computer. So those instructions, those are what makes the computer do something. And the programmer is the person who writes those instructions. You see what I mean about Chapter 1. What is a CPU? What is main memory? What is secondary memory? What are input devices, output devices? Read Chapter 1. Main memory is volatile, meaning that it's erased when the program terminates or computer is turned off. And for a while, in the 80s, they played with something called bubble RAM or bubble memory, which was memory that even if you interrupted the power to it, it would maintain all of its information. So if you unplugged your computer and you plugged it back in, then it would just be exactly like it was. Kind of like the way your phone is, you know, you turn your phone off and you turn it back on, but you're not really interrupting the power when you do that. But bubble RAM, bubble memory, was extraordinarily slow, and it couldn't really be sped up, and it was expensive, so it was lost as a technology. Who cares? So memory is volatile, meaning that all your data that you type into your computer is lost when you switch it off. So you have to have some kind of secondary storage as well. Your phone has RAM in it, but it's also got flash memory. Pretty much like the USB sticks that you stick into computers nowadays, you know, instead of floppy drives. Because you have to have some place for non-volatile stuff. Your applications need to be non-volatile, else you'd have to re-download from the App Store every time you turned it on. It'd be a real drag if you typed in a paper and then you shut the computer off and it was gone forever, and the next time you wanted to make a change to it to print it out again, you had to type it all in again. You may as well just have a typewriter at that point. So you have to have permanent storage, semi-permanent, and then you have to have the volatile. The volatile RAM is where the data sits as it is being processed. That's the silicon chips that sit there inside your computer. You have like 4 gigabytes or 8 gigabytes or whatever. And then the non-volatile, the storage device, is what feeds stuff into the memory. You can load data, load MP3s into memory so that they can be played, load pictures up, load applications, that kind of stuff. Every byte in memory is identified by a unique number known as its address. So if you had a computer that had 30 bytes in it, pretty small, they would be numbered from 0 to 29. Each byte holding a number. We haven't talked about what a byte is. Talked about it enough so that y'all who've taken fundamentals or the Java course have heard more than enough about it. A byte is a value between 0 and 255. And so by stringing those numbers together, you can get larger, more complex numbers. You can get larger, more complex data types. Text, for example, is just a sequence of bytes. And we'll talk about that another day. But just think of RAM, your random access memory, as 4 billion little boxes, each one that can hold a number between 0 and 255. Why is that important? At a certain point, we will be modifying what are known as arrays, which are contiguous pieces of RAM, where you could store one thing in that one, and then you could store something completely different that one, something completely different in that one. So we'll be coming back to the idea of memory as a sequence of storage places. Secondary storage. Those are your floppy drives, your disk drives, your CD-ROMs, your DVD ROMs, your tape drives, if you had such a thing, your flash drives. And nowadays all phones have flash drives, and a lot of the more expensive laptops don't have hard drives. They have solid-state drives. Why? Because a hard drive is a spinning mechanism with a magnetic, platter on it, or a whole bunch of magnetic platters. It's slow to access. You have to wait for that thing. I mean, that thing is spinning like 96,000 times, per minute, but still, it has to wait for it. The heads are sitting here, and they read. They scoop up the bytes that you need, and then there's significant lag in reading from a hard drive, no matter how fast the mechanisms are. So, solid-state drives load more quickly. They don't have the moving parts that a hard drive does. My PowerPoint. Here we go. No, that's not my PowerPoint. There we go. So input devices are things that send information into the computer, not just the obvious ones like keyboards and mice and stuff like that, but you can have sensors. You can be sure that those self-driving cars have lots of sensors, LiDAR, LIDAR, laser, whatever, based radar, so that they can tell how close things are or whatever. And your car has temperature sensors to determine, the temperature of the components that are going into it, and pressure sensors so that, you can flash a light on your dash if your tires are getting low or whatever. Anything that sends data into a computer is known as an input device. Categories of software. You have system software. The system software is the programs that manages the computer hardware and enables programs to run on it. So your operating systems are system software. Your utility programs. What's a utility program? It's something that manages the computer. There are disk drive formatting utilities, disk utilities and stuff like that. The only time you ever mess with that kind of stuff is when you actually want to make changes to the way your computer works. You want to add an account so that your mom can use your computer, but you want to limit her access. You go to the accounts thing, you make a new account called mom, and you don't give her admin privileges. Admin privileges, all those words, those are managed by the operating system, and you use utility programs to manage them. And then software development tools. Software development tools are things where you can write programs, like Visual Studio. Then there's application software. Word processors, games, programs that solve specific problems. If you're an airplane designer, you need software that will simulate airflow, over the plane or whatever. And people spend lots of money writing super sophisticated software that will run on massively parallel systems to simulate things like nuclear reactions and weather simulators and such like that. Programs and programming languages. A program is a set of instructions. To create those instructions, you need to have an algorithm in mind. An algorithm is a series of well-defined steps. You want to calculate pi, there's an algorithm for it. If you want to calculate how much you've spent this year, or what your budget is, there are algorithms for that. You take an accounting course, you figure them out, and you can implement them. Algorithms for converting, Fahrenheit to Celsius. Algorithms for figuring out, if you burn this many liters of gasoline, how much carbon is produced, how much, oxygen is produced, and how much CO2. You don't produce the oxygen, you burn it. Sorry, my mistake. For example, the algorithm for calculating gross pay. You could write a program that did how many hours did you work? Then you let the user enter a number of hours worked. When they enter that number, you store it in memory. You store it in a variable. Display a message on the screen asking how much do you get paid per hour. Then you wait for the user to enter an hourly pay rate. Once the user enters that number, store it in memory as well. Then multiply those two numbers together and store the result in memory. Then display a message on the screen that tells the amount of money earned. The message must include the result of the calculation. Now, am I going to give you an algorithm in this form? Probably not. That's way too much, isn't it? You know how to calculate our pay. You know, it's number of hours worked times hourly wage. If I give you an assignment based on that, I'm going to say write a wage calculator, ask you how many hours to work, ask the hourly wage, and produces the result by multiplying one by the other. You know, that's like 2 sentences rather than all this. But this is how you solve the problem, step by step. This is not a programming code. You can't give that to a computer and have it do it. You're the programmer. Turn the algorithm into the language of your own choice. Machine language. Computers only execute machine language instructions. Just series of numbers that the specific brand of CPU in your computer is expecting to receive. So that algorithm is not a series of numbers that can be fed to a CPU that cause it to do things. It has to be turned into a program. The program, you still don't want it to be machine language, which is just all zeros and ones or letters and numbers. So what you want is to be able to do something like this. You know, int hours is equal to 30. Float wage is equal to $8.95 an hour. Float salary is equal to hours times wage. And then display, you know, salary this week is all of that. This is what our programming code looks like. We don't want to have to type in ones and zeros. There's an intermediate form between zeros and ones in this called assembler. Might go find a picture of it, show it to you. So you have to have something that will translate this into this. And you Java programmers heard me just talk about turning it into an intermediate form and blah, blah, blah. In this language, what happens is you run a compiler. The compiler converts this code. We're going to call this source code. Why is it called code? Is it really a code? It's not encryption, but it is a programming language. I guess it's kind of code-like. So the compiler turns the source code into what's known as object code. Object code is the machine language, but it's not ready for the computer to run. Then the linker runs and links the object code to make an executable. Why do we say link the object codes? Because you could write a program that has 40 or 50 different C++ files in it. Sophisticated games, you know, the games that cost millions of dollars to develop nowadays to run on your PlayStation 4 or Super Duper Xboxes or whatever, you can be sure that they have hundreds upon hundreds upon hundreds of files that are all coordinating to work together. Each one of those files gets compiled into its own little object file, and then all of those are linked to make an executable. And we usually don't worry about that too much. If you have a nice tool like Visual Studio, you just click the Start button, and it does all this for you. A lot of classes, well, this is how they used to teach it. You would run a command line, and then you would run a compiler on your program. I want to compile my file, test.cpp. It would compile it and turn it into an OBJ file. And then you would do, I want to link that object file, and I want you to make an executable called test.exe. And then once you were done with that, you could run your program. Obviously, it's kind of nice that whether you're using Eclipse or Visual Studio or something like that, it's all handled by the development environment to make it easy to use. So machine language is just a series of numbers. You don't write programs in machine language. That went out in the 40s. So you use programming languages. Programming languages are things that get turned into machine language. So a low-level language is something that's used for communicating directly with the computer hardware. It's written in machine code, zeros and ones. And there are high-level languages, High-level languages are what we use. Java, Python, all the different versions of C, C++, C Sharp, and that kind of stuff. Called high-level, and it's English-type languages. It's weird that almost all programming languages are written using English words. Yeah, even if you're a Polish inventor, you're still writing in English. You may call your variables Polish terms, whatever the Polish term for salary is, or whatever. But you're kind of learning English just when you learn a programming language. There are intermediate terms, intermediate form of language. Let me see if I can find hello world in many languages. I used to upload this. Okay, some of y'all know Python. This is how you print the words, hello world in Python. You just have the word print, parentheses, quote, hello world, end quote, in parentheses. That's how you do it in that language. Let's look up, some of y'all are taking Java. Let's go see what a Java hello world looks like. Here it is. It's a little bit longer. Class hello world, static public void main, blah, 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 system.out.println, hello world. Again, you have that word print there, You can look at that, and even if you don't know what all the rest of that stuff means, you know that it's printing something. Let's look up C++, our language. All sorts of different versions of C++, aren't there? Alrighty, hello world, written in C++. If I zoom in, I'm going to lose my place, but we can always find it again. Alrighty. There we go. There's some include statement up at the top, and then there's this word main, and then it says C out, blah, 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 hello world, blah, blah, ENDL. So that looks a little maybe more cryptic. It doesn't have the word print, but you can figure out, okay, somehow I'm going to see that C out, and it's going to be displayed. So you can see that languages, they differ from each other, but they have the same concepts. Now we're going to find a language that's called assembler, and there are 8 million different versions of assemblers because there are 8 million different types of chips out there.
What are the less than signs for?
The less than signs say, and this is unique to this language, take these strings of bytes and send it to what's known as the console, which is the screen. And the way that the less than symbols point say which way is the data going. The data is going to console output. If we let the user type in something like their name, we're going to put something else here because you're not writing to a screen, you're reading from something, and then you're going to have the arrows go the other way, and they're going to go into a variable so that they can store the name. And we'll do that before not too long, right here in the class, that payroll algorithm. So assembler. The first PCs, IBM's PC, came out on the, not the 6502, but the 8086. Let's see if I can find that. No. Alright, it doesn't matter what kind of assembler it is. Here it is. How to say hello world. Now if you're looking at this, each one of these words is just a mnemonic for a number that the chip would understand. So move is operating code 41. And JSR, whatever that means, is operating code 42. And BEQ, whatever that is operating code 43. And so these numbers, followed by these numbers, are fed to the CPU in order to get it to do things. Am I going to try to convince you that I even understand what this is doing? I learned a flavor of assembler that I don't even see listed here for some reason. Intel. There we go. There we go. I could tell you what this does. But anyways, so you're moving some data around, and here's the data that you're moving around, and eventually you trigger something in the hardware that causes it to be displayed to the screen. Do you want to program in this in order to just print the words hello world? No. Assembler is just one step above zeros and ones. And so we don't want to do that. We want to write in a high-level language, not a low-level language. So from a high-level program to an executable file. This goes into even further detail about what happens. This is C++, C specific, not just C++, but C and C# specific. You create a file, like with a text editor. All a program is some text that you've typed into it. You could create it with Notepad, for example. You couldn't do it with Word unless you saved the Word as a text file, because a Word file has all that formatting information, fonts and boldface and stuff like that. But if you saved it as a text, that's all a program is text file. That's the source code for it. You run something called a preprocessor. I'm going to ignore that. You run the compiler that turns the source code into machine instructions. So whenever I say compile the program, that's what I mean. Click something on Visual Studio or whatever your environment is that tries to turn your program into machine instructions. Then you run a linker that hooks all those machine instructions together to make an executable file. Fortunately, nowadays, steps B through D are all performed by a single command or button click. If there's a problem at any step in the way, the program will not build and we cannot run it. So if there's a syntax error, if something is spelled wrong or the syntax is wrong, we have periods and semicolons in the wrong place or whatever, then it will not compile. Since it cannot be compiled, it cannot be linked. And since it cannot be linked, it cannot make an executable, which cannot be run. So that's why I put in my syllabus, you have to have something that actually compiles. I won't accept it if it doesn't make a working program. So what is an IDE? Integrated Development Environment, such as Visual Studio. There are other ones. They talk about Turbo C++. I don't know if anybody still uses that. There's Eclipse. Eclipse is very popular. It's well supported for a lot of different environments, Linux and stuff like that. And then there's another one available on the Mac. And why is it called an integrated development environment? Because it gives you everything. You have a text editor, and you have buttons that'll build and compile it, and you have something that'll manage your project. So if you have more than one file in it, you can switch between your source files just by double-clicking over here. And then you have all these menus that'll let you debug your program. If there's a problem with it, you might want to step through your program line by line, watching the variables change and stuff like that. So it's integrated. It brings it all together. You're not just at a command prompt typing in CC for compile and link for link and stuff like that. Instead, you get to do it all in a nice visually interesting way. Interesting is not the selling point. The selling point is that it's very powerful and it lets you develop stuff much more quickly. What is a program made of? Keywords. Don't know why it shrunk that. Programmer-defined identifiers, operators, punctuation, and syntax. The keywords are words like if and while. Those are the things that define the syntax of the language. Every language has its own set of keywords, but they all overlap a lot too. Almost every language has an if in it to make decisions. If temperature is less than 32, print brr, I'm cold. That kind of stuff. While x is less than 32, keep saying brr, I'm cold. That's stupid, but you have a braking algorithm. You're trying to stop your car. While speed is greater than 0, continue to apply brakes. That kind of stuff. So you need a while word, and you need an if word to implement the logic, and then there's all sorts of other keywords. Identifiers, those are your variable names. Salary, age, name, hourly wage, weight, height. All of those things are what are known as programmer-defined identifiers. Now that's a mouthful, so you just call them variables. There are other kinds of identifiers too. Functions. You may write a function that prints out, somebody's mailing address. You give that function a single name so that your code can call that function. That name is its identifier. Your program calls that function, it prints out a mailing address. You kind of build modules for your code then. You break it up into you break the problem up into functions so that you don't have to write one big program. You write a set of modules that work together. And then you have a team of people working on those modules if it's a large program. Word, Excel, those things are huge programs, and you can be sure that there are very large teams of people. You know, Madden and Call of Duty and all those, Dragon Age, those are huge programs. So there are going to be many, many, many modules in them, and they have to have tools for managing that stuff so that multiple people can work on the same project. Because what happens if two programmers sit down and they rewrite the mailing, the mail label module? Well, I turn mine in, and then you turn yours in, you erase my changes, and I get unhappy. So you use tools that will lock that module so that only one person is making a change to it. But that's software engineering practices, that's not programming. Here's an example program, but we're going to write that, so I'm not going to spend much time on it except to say, here's some keywords. Reserved words. Int is a keyword. Using is a keyword. These are words that you cannot use yourself. They are reserved to the language. They define the syntax for it. Return. Then there are other words that you get to define. The identifiers, the variables, the hours worked, the rate, the total pay. Those are all identifiers. Those are all variables. You get to pick those. You could just call them X, Y, Z, or you could call them Huey, Louie, and Dewey, or Bugs and Darth Vader. And you're not going to do stupid names like that. Instead, you're going to use names that are meaningful, or else you won't understand what the program is doing if you come back and look at it 2 weeks later. Yes, sir?
Do you not get syntax errors whenever you do like double space hours? Would you not have to do that to score anything there?
This is good code. This would work if we copied and pasted it. So,
No, I'm just asking, is that like something that exists in C++? Do you get syntax errors for spaces?
absolutely you can get syntax errors, not for spaces. As long as the keyword is separated from the variable name, that space is necessary, but this one between the comma and the next variable name is not. The one between that comma and the next variable name is not. That space is not necessary, that space is not necessary, or you could pad them out. If you wanted to say double hours, you could do that. And we'll muck with mangling the format of our code to illustrate that point. That's what's known as white space. This entire program could be written from here to here in just one line of code. Or not one line of code, but in one. It would be a very long one. You could just delete all the carriage returns. White space makes the program easier to read and understand. That's why they put so much space in here, to make it easy to understand. They put in blank lines to kind of break it up into paragraphs. So keywords are known as reserved words. They have special meanings. They cannot be used for any other purpose. You can't say while is equal to 3 or if equals Joe, because while and if are already reserved for the syntax of the language. So the word using is a keyword. Using the word namespace, int, double, return, all of those are keywords. And we'll use those real quick. So identifiers are names made up by the programmer. They're not part of the C++ language. C++ doesn't know what a salary is or an hourly wage. It's up to us. We define what those are, and we imbue those things with our own meanings. They represent things. The variable represents a memory location that contains some data. Another form of identifier is a function, like I said. We have several identifiers in this sample code. And like I said, I'm not showing the sample code because we're going to write our own version of it. Better than just copy and paste. Then there are operators. Operators are the mathematical symbols. There are a lot more operators than just addition, subtraction, multiplication, and division, though. Those less than symbols you saw, those are operators. They're very specialized operators. They're called stream insertion operators. They send a stream of data to be displayed on the screen, or they accept a stream of data from the keyboard or off the internet or something like that. And this may be making it sound complicated, but once we start typing this stuff in, it's going to start falling into place, just like putting bricks in a chimney. And then there's punctuation, just like in the English language. Characters that mark the end of a statement. Semicolons mark the end of C++ statements. Some languages do not have terminating punctuation, like Python. A lot of them do. Or separating the items in a list. You have 3 variables being created, you put commas between them. They'll separate the items in that list. So the punctuation in C++ consists of, but is not limited to, commas and semicolons. It also includes parentheses, those curly braces that mark off blocks of code. Let's stop lecturing, let's start coding. Open up Visual Studio, and we're going to do something very similar to what we did last time. We're going to create an empty C++ project and then add a program file to it. Now I have something left over from a previous class, C++, so it looks a little bit different. New project. And I know some of y'all may not have Visual Studio open yet, so I'm going to go slowly. Just choose New Project. Give your project a name. I'm going to call mine August 24. It's supposed to be a console application? No, because that's a C# choice. I want a C++ choice. This is going to be confusing, swapping between the two for me, not for you. Visual C++ empty project. That's what you want. Then I'm going to click OK. So I chose Visual C++ empty project. It churns. Since it is an empty project, it doesn't have any source code files yet. If you do not see Solution Explorer, it's because it's been hidden or closed or something like that. If you want to bring it back, you choose View Solution Explorer. You need to have the Solution Explorer around when you're switching between files or making new files or stuff, but if you find it's taking too much space, you can minimize it like that. Well, maybe that's a bit extreme. Or you can always just close it and bring it back when you want with the View menu. And if you look, there's a lot of things under the View menu. If you want to see an error list or the output of your program, or all sorts of things here. All right, so with the Solution Explorer, I'm going to right-click on Source Files and do Add New Item. And let's write a program called payroll. I don't care if you just turn stuff in with the name source.cpp, but it's cooler if it's got a better name. And what do I mean by cooler? If the name indicates what the program does, then it's more useful. Gives me a clue right away, even before I open the program, that it's some kind of payroll calculation. Is the name important to the computer? Does the computer care that we called it payroll? No, you could call it, uranium-238 or whatever, and it would run just as well. You can name your applications anything and they will still run, but names like variable names and application names and stuff like that are for the people. So we come up with our blank screen here, and we have some boilerplate that we're going to type in, and you're going to get tired of typing this in perhaps. You may wind up typing this in a lot. You probably will. If you want to, you can save this stuff as a text file and paste it. But it doesn't take too long to type it. # include iostream. And notice that it's trying to help you type this stuff. It's filling in possibilities for you. And even though we're probably not going to use strings, I like to always include strings anyway. So include string. What these are doing these are bringing in libraries to use. iostream is what gives us those less than, and greater than to let it display stuff on the screen and to read in from the keyboard. If you're writing device driver software that doesn't interact with the keyboard or display stuff on the screen, you might not be including iostream. So it's like C++ has a nucleus of stuff, and then it's all the libraries that you add on to it that give you a lot of power. And there are a lot of libraries. Libraries for drawing graphical user interfaces with menus and stuff like that, or for writing internet applications that need to communicate to servers and stuff like that. Okay, so we have those two words. The # thing, that's called a preprocessor command. I'm just going to make a note of that in a comment. Pound sign indicates a preprocessor command. Why is it called a preprocessor? The preprocessor gets run even before the compiler. And what it does is it goes in and grabs this file and it inserts that file behind the scenes, we never see it, into the file that's about to be compiled. Then it gets compiled. So the preprocessor can do all sorts of stuff to your code even before the compiler sees it. We will be putting #include in every program we write. We won't be doing much with the other preprocessor commands until we get further along in the course. There are some. There's #define. Don't type this. There's #ifdef. There's #pragma. We'll know what all those mean eventually, but not now. Okay, so a preprocessor command is something that happens before the program is compiled. #include means bring in another file and insert it there for the purposes of compilation. That way we don't have to have 1,000 lines of code that implement I/O streams right in our program. You know, we don't want to have to write all that stuff or copy and paste it into this. We just want to be able to write a short program that uses the keyboard and shows stuff onto the screen. So we use that and it brings all that code in, but we don't have to see it. All right, then we're going to tack on the word using namespace std. Notice the color coding. This is another cool thing that integrated development environments, not innovative, I guess they were innovative at one time, IDEs do. Color code, syntax, context-sensitive color coding. I don't know the proper term for this. But keywords are colored blue. Comments are colored green. If you're colorblind, then some of these colors may be different, but hopefully you can at least distinguish, you know, even if, you know, hopefully they are not identical shades. Do you need colors in order to understand programming? No. Did people in the 60s have colors? No, they had green and they liked it. Okay. And so, but it helps us. Anything that communicates more information at a glance is an advantage to the programmer, and that includes the color coding of the various words. Okay, more of our boilerplate. Void main, these are parentheses, and then under the parentheses I'm going to use curly braces. Sometimes I may just shorten that to say brace. The British are a little bit different, and they use the term brace for a lot of symbols that we don't, I think even the parentheses. Yes, sir?
Is it possible to start the curly braces right after the parentheses?
Okay, uno momento
Function the same way?
question. Okay, so why did I do this? Why did I put that curly brace on the next line? That's not necessary. Some programmers do it like that. That's one style of brace positioning. This style is known as block positioning. And you'll see me use this consistently throughout it. However, some editors try to enforce that positioning. And sometimes I'll kind of waver back to that when I'm trying to get more code on the screen. And that's going to make more sense as you see me type more. This is an example of white space. This is the same thing as this. I haven't changed the program. I've just changed the way it looked. This is the same as this. I still haven't changed the program. I've just changed the way that it looked. White space just makes the program easier to read. And what is white space? It's using tabs and blank lines in the space bar to make things a little bit easier to read. Okay, so this is our code block. Whenever you have a pair of braces, it defines a code block. Let's put some code into it. We're going to write that payroll program. We want to ask the user some questions. We want to perform some calculations. We want to display the output. So, in order to calculate somebody's pay, what do we need to know? We need to know their hours worked and what else?
The wage.
The wage, right. And then if we want to get all technical about it, we need to know if they get, you know, if they're capped at 40 hours or if they are allowed overtime or stuff like that. We're not going near that stuff yet. But let's declare a couple of variables. Are all of these going to be whole numbers? Because we have several different data types available to us. Don't type this. Or I mean, if you want to, you can do it as a comment. But there are integers, which are whole numbers. Unbers. There are floating point numbers, which have decimals in them. And then there are strings. This language uses lowercase. Is your number of hours worked always going to be a whole number? I don't think so. You might work 3.75 hours or whatever. So we're not going to use any ints at all. I think in their example they make the hours an int and then the wage a floating point number. We're just going to use floats the whole way. So let's declare some variables. We're going to call one hours. We're going to call another one the wage. And then the last one the salary. So what we're doing here is we're declaring our variables. Declaring a variable means giving it a name and then giving it a data type. We're saying that hours is not just going to be limited to whole numbers, but that it can accept decimal points as well. Whenever you define multiple variables of the same type, you don't have to list them one per line like that. We saw an example in our code of where they did it like this. They did float hours, comma, wage, comma, salary. Does the same thing because it doesn't stop building these variables until it hits the semicolon, the punctuation at the end of the line. I kind of like putting them on their own lines. Why do I like that? Because I could put comments about what these were. I could say this is the hourly wage. No, hours worked this week. And we could put a comment here that says pay earned per hour. And then we could put a comment here that said total salary for this week. That's why I like listing all the variables one per line. On the other hand, screen space is at a premium for me, not for y'all so much. But I like to have a lot of code up here. Some of y'all will be typing in some of the stuff at the here. Some of y'all will be typing along, you know, you're faster and you're here. And if I fluff things out like this with a lot of space, then I have to scroll up and down for everybody to see everything. But I'm going to leave it like that. But for example, if y'all hadn't typed this stuff in and you needed to see it, and I'm already down here adding this stuff, it's kind of a problem. It's always okay to raise your hand and say, can you scroll up? And I'll do it. And if you're really lost, ask and I'll print you out the code. So you have tools available to you if I'm going too fast or whatever. If I am, just slow me down. And what I need to be doing is wandering around and making sure that everybody is on the same page. The program doesn't do anything yet. All it does is declare some variables, so if we run it, we're not going to see anything. I'm going to go ahead and build it. I'm going to choose Build Solution under the Build menu. If I have an output window somewhere, it should say that the build succeeded. There it is. Eventually, if I scroll down the output window, I will see build 1 succeeded, 0 failed. If I don't have an output window, I can't find it. I can find it with View. View Output. So if you want to see the results of your compiling, say I'd accidentally closed it, you do View Output and you can see them. Along with the output, there's something else known as an error list. If the error list wasn't displayed, you'd find it like this, View Error List. Right now there aren't any errors, but there are some things listed down here. If it's got a little caution sign, it's not an error but a warning. It's saying, hey, I've noticed something that you may want to attend to. And in this case, it's saying, oh, you created these variables, but you didn't do anything with them. So they are, quote, unreferenced variables. They were never used. If they were never used, why create them? They would just confuse the next person who came along to modify your code. The reason they're unreferenced is we haven't used them yet ourselves. Okay, so I'm going to run the code. I'm going to come up here and press the green arrow that says Windows, Local Windows Debugger. You can also do that under debug, there's several choices here. Start debugging, start without debugging. For the vast majority of time, just wailing away on that green arrow is going to work. It did something and it closed the window already. That's because the program's not doing anything. Okay, so when I talk about boilerplate, what you could do is you could take all of this stuff here from there to there, and you could open something like Notepad or another text editor. And everything from there to there and there to there, you could store in a text file so that the next time we start a program, you could just open up, you could make a new file, you could copy from this, paste it in your new one, and then as I'm sitting here saying, include iostream, include stream, you're ahead of the game. You've already got it. So I'm going to do that right now. I'm just going to save this as boilerplate. Next time we type this stuff in, I'm going to encourage you to do the same thing. Stick it on my desktop where I find it easy to find. All right, so now I can get to my boilerplate if I want it. I'll have y'all do that next time. By the way, if you want line numbers, I have line numbers down my side, and y'all don't. Not really strictly necessary, but when we were looking at the error list, I don't see them now. Let's rebuild it. Rebuild the solution so we can see our errors again. They give line numbers, 17. So you could scroll down and find it. Do you need those line numbers? No. Why? Because if you double click on it, it takes you there anyways. If you want the line numbers though, if you think they're cool, I may disable them. They take up screen space. You go to Tools, Options, scroll down until you see Text Editor. Click the little arrow next to Text Editor and choose All Languages. And once you do All Languages, you see line numbers. You can turn them off or on. I'm going to turn mine off. Why am I turning it off? Because I can just double click on an error and it'll take me straight there. Okay, we have our variables. Let's use them. Let's tell the user what they need to do. Welcome to the payroll calculator. I think we mentioned last time, if I'm not mistaken, that you can end a line of text. You want it to go to the next line. That's called a carriage return. You can either use this thing that says ENDL or you can use a \n. If you do type ENDL, don't type END1. That's not a 1, it's an L. It stands for end of line. I'm just going to leave \n. I tend to use \n if I already have an open string. In other words, I have a closing quote that I haven't closed yet, because it's just shorter. What does /n mean? It means go to the next line. So as soon as it prints this out, it's going to say, welcome to the payroll calculator. Now let's ask the question. How many hours did you work this week? And I think I'll put a space there. You can leave the space out and then you'll see what happens. Is it important? Yeah, you may like it with the space. I'll show you what it does. Actually, I'm going to leave it out. And then when you run it, you'll see why I wanted it there. All right, we've displayed 2 messages. Now let's do, and by the way, guys, I do want y'all to upload this, so I hope everybody is typing this stuff in. So CIN into hours. What this says is, okay, Cout stands for console output. That's a fancy way of saying the screen. Send this data to the screen. In other words, show that message. Then send this data to the screen. Show that message. Then let them type it in. Console input, CIN, means let them type stuff in from the keyboard. They type some stuff in. It gets stored in that variable. So at this point, we have a number in that variable. We have a number, whatever they type. They worked 40 hours. We're going to put, it stores 40 in that variable. Now I'm going to run it again. Build solution. Is it strictly necessary to hit build solution every time? No. Usually you can get away with just hitting the green arrow again, but I like rebuilding it each time. I find that to be more reliable. Let's say I do the running, and now it's actually displaying something. I need to get this out of the way for y'all who are typing still. It's showing some stuff on the screen. Good. our program is taking shape. This is a very common programming mode. You start off small and you keep adding to it. If you're going to write a video game about Pac-Man running around on a screen, you don't want to wait until you've written the entire program that's supposed to be displaying dots and have 4 ghosts running around like that. The very first thing you do is just to make sure you can display something on the screen, anything that has some colors. So you draw a yellow circle. All right, I've drawn Pac-Man. Then you make it so that that yellow circle can move one way or another on the screen. Then you decide you want it to be animated, so you modify your program so that the mouth is moving on it. You start small and then you snowball it into something larger and larger, and you compile often. You don't want to type for 2 hours before you test to see if your code can even compile. You want to catch your syntax errors early. All right, so when I ran it, it says, welcome to the payroll calculator. How many hours did you work this week? Wow, I was really busy. I worked 100 hours. It's done. Why did it stop? Because we hit the end of the program right there. And it closed the window. We don't want it to close the window. So you Windows users, not your Linux users, are going to add a system call here at the bottom that will call the pause command. And I know I talked about that last time. There are other ways of handling this problem. This is just a very common, easy one. Easy fix. If that's not going to work for you, you can do this. We could do this instead. Cout, press enter to continue. And then we could do cin into some variable. We would have to create a variable. I don't want to do that, but if you find out you're using Linux and it's closing your window before you can see the output, you'll want to do something like that. Find an equivalent solution. Okay, so now when I run it, how many hours did you work? I worked 100. Press any key to continue. Okay, great. I'm getting to see the answer. It's not producing an answer yet, but at least it's not closing the window the second they hit enter. We've gotten the hours. We need to get the wage now. So, cout, what is your hourly wage? Cin into the wage variable. We told them what to do. Now we're letting them do it. And any number they enter is going to be stored into wage. What if they don't enter a number? What if they enter, I like pizza? Well, the program's not going to work. Alrighty, are we going to ask them for their salary? No, we're going to calculate the salary. And as a matter of fact, what we really want to do is to describe what the program is supposed to do. We are going to scroll up to the top and add a comment block. And I want you to do this for every program. Put your name, put your date, and a short description of the program. Payroll calculator asks for hours and wage calculates salary. There'll get to be a point where I start counting off if your stuff doesn't have that up there. For in-class assignments, I don't count off. Although if I take the time to type it, you may as well. But homework, I do want you to remember to add the comment block up at the top. Professional programmers do add comments to their code, and so that when they come back to it later, they understand what it's doing. Now these programs that we write are so simple that sometimes I forget to add comments. I'm going to scroll back down to where we were. See, here's a comment that says declare our variables. Let's add a comment that says what the next section of code is. So underneath all those floats, we're going to put another comment. Get our data from user. Now, underneath those things, but before the system pause, we're going to have another comment. And the comments are just to explain what the program's doing. It doesn't change the way it works. Calculate salary. If we were really cool, we'd put the formula there, but it's going to be pretty obvious when we type salary is equal to hours times wage. There gets to be a point where you're putting too many comments in your program. If your code doesn't have any comments at all, you're slacking off, you're not being professional. If you're putting in a comment for every line of code, you're being an overachiever and you're making your code hard to read. Just find a happy medium. All right, now that we've calculated the salary, we're going to add one more comment that says display results. And I'm well past the point where I should have wandered around and made sure that y'all weren't having syntax errors. I apologize for that. Let's go ahead and display the results. So, see out your, or let's say, you earn, and then followed by a space and a quote. Now let's print out their salary. Followed by a couple more arrows because we're going to put some more text on the screen. Dollars this week. Slash in. Go to the next line. Okay, so you can see that as I make things easier to read, I'm also making the program so that we would have to scroll up and down in order to see it all. So if I was concerned that y'all weren't keeping up, I might have had to do this. I might have had to take all the blank lines out, maybe even remove the comments. This is called removing the white space. We could get the whole thing probably to fit on one page if I deleted all the comments. I'm going to undo that. White space is your friend. I'm not going to fail you if you don't put white space in your programs. But it makes it easier to read. Strongly recommend you get in the habit of trying to make your code as readable as possible. It's like if you're writing a story, but you don't put any spaces between the words, then the reader's not going to be able to read the story very well. All right, I'm going to run it again. Build solution. Then I'm going to run it. I didn't see the output. Rebuild solution. There we go. 1 succeeded, 0 failed. Local Windows debugger. Welcome to the payroll calculator. How long did you work? I worked 40 hours this week. What is your hourly wage? Well, I earn $100 an hour. Aren't I lucky? Okay, I earned $4,000 this week. Seems to be working. Test your program with garbage data. There's a saying, garbage in, garbage out. How many hours did you work? I like pizza. What is your hourly wage? You earn $1.1 quadrillion. Yeah, okay, I like that. I want to see them. Unfortunately, if you ever get a paycheck that's vastly huge, or if you get a check from the government, it's not legally yours. Don't go and spend it all. Later, if you get a huge tax return, the IRS is going to say, oh, we made a mistake and you're responsible for giving us back all that money. And you've already bought yourself a Ferrari. Anyways, garbage in, garbage out. I typed in, I like pizza, and so I got this absurd result. You can make programs that are more careful than this, that demand that they type in a number, and if they don't type in a number, that's called input validation. Like if you ask somebody for their birth date, and they type in something that's not a real day, then you want to catch them on it. If they type in an address, but they have a zip code that doesn't exist, you want to catch them on that. That's a bit more than what we're looking for, but we could at least check to make sure that the zip code was 5 digits. Okay, I'm going to pause the recorder and wander around and make sure y'all all got to this point. Resume recording. So this is our homework using the same techniques. Homework. Ask them for their weight in pounds, display their weight in kilograms, I guess because they're traveling to France and they need to know. The conversion formula is kg is equal to pounds divided by 2.2. Close enough, it's not exactly. That makes sense? I may wind up asking you to use Xcode instead, which is Apple's version of C++. Dropboxes.
Mr. Thompson,
Yes, sir.
you use double in C++ as well?
Yes.
What's the difference between double and flip?
One is 64 bits wide and one is 32 bits wide, so a double can hold a much larger value.
So would it make sense to just use double all the time?
You may as well. Certainly for your Java class, just use double the entire time. And y'all will learn what we're talking about here. Okay, so payroll program was our in-class. I'm going to rename Hello World to A because I keep forgetting this semester for some reason that I always like the in-class tutorials to be letters and the homework to be numbers. That way, if you say I need help with program 1, I know which one you're talking about, rather than wondering if it's the in-class. Okay, so homework 1 is conversion pounds to kilogram. It will be due next Wednesday. However, we're not going to get to meet before Wednesday. I mentioned that I'm not going to be here Tuesday. Is that correct? Okay. I'll post a notice as well. I'll text y'all, absolutely, to make sure. Okay, so anyways, I'm not going to make this due Tuesday. I'm going to make it due at the end of next week so that we have one more class period before it's actually due. And again, if you're having trouble getting your C++ development environment going, then I will understand for this first one. Alright guys, so if you remember how to upload the CPP file, remember that you could either zip the folder or you can just give me the CPP file. That's probably the faster way to do it. I'm happy with either one. Go and find the Dropbox for B, refresh your Dropbox, and give me either the CPP or the zip file. And if you don't remember how to do that, I'll wander around and help you. Once you get that done, I will take roll based on what y'all upload. So do upload something or else you won't be counted as being here. Y'all aren't seeing these, I just forgot. Because as of this semester, everything is hidden until you go and unhide it. I apologize for that. Feel free to throw a shoe at me. Alright, if you refresh your Dropbox now, you should see all 4 things. Is that correct? Alrighty. Okay, so I'll see y'all next Thursday.